Hi guys, in our first example about gas properties relating to kinetic molecular theory, we're going to start with a straightforward question that deals with the number of moles and how we can manage to find the molar mass or the number of moles by using Graham's law. So if you recall from our videos, Graham's law states that the rate of fusion of two gases is inversely proportional to the square root of its molar mass. So if we want to write it as an equation, Graham's law would be this. Sorry. So Graham's law, you have to take into account that Graham's law deals with several different ratios over here. It could be the ratio of molecular speed, effusion rate, effusion time, distance traveled by the molecules, and amount of gases fused. So any of those things that I mentioned, they could be equal to this statement. Now, one thing that I'm going to discuss later in another example is for effusion time. Now, when you're talking about effusion time of two different molecules or elements, we do not use the inverse of the molar masses. We actually use the molar masses as they are present in this situation. So anyway, we'll discuss this in our other example. In this case, we have the amount in moles of two different gases and the inverse, square root of the inverse of their molar masses. So over here, we have 4 times 10 to the power minus 4 moles of carbon dioxide effuses through a hole in 95 seconds. How much hydrogen would effuse given the same conditions? So we have the same conditions, same temperature, same pressure, but we have hydrogen now instead of carbon dioxide. So how much hydrogen would effuse given the same conditions that we have over here? So in the same amount of time as well. So in this case, let's take Na as hydrogen over Nb is carbon dioxide equals the molar mass of B, which is carbon dioxide, is 44 grams per mole over hydrogen is 2 grams per mole. So now we also know the number of moles of carbon dioxide, so we can actually just write it over here. So that would be 4 times 10 to the power minus 4 moles. So now, in order to find the hydrogen number of moles, we isolate the number of moles of hydrogen. So now we have 44 over 2, so that comes up to 22. And then times 4 times 10 to the power minus 4 moles. Now, one thing you have to know is that when you're doing square root is unitless. So whatever answer you get, it's usually unitless. So when you do this, 22, a square root of 22 times 4 times 10 to the power minus 4, if we do the calculation for it, so square root of 22 times 4 times 10 to the power minus 4, that should come up to 1.88 times 10 to the power minus 3 moles. So moles of hydrogen gas. Now, let's take a look at the numbers. Here we have 4 times 10 to the power minus 4 moles, while for the hydrogen we had 1.88 times 10 to the power minus 3 moles in the same exact conditions, same temperature and pressure. So these answers should make sense to you. Why? Because we know that the speed of molecules is related to molar mass, right? So the lighter the molecule is, the more likely it's going to be at a faster speed, the more likely it's going to effuse fast. It's going to effuse into much higher amounts in the same time. So at 95 seconds, less carbon dioxide will diffuse compared to hydrogen because hydrogen is smaller. So these answers should make sense to you. If you actually got a number that is smaller than the carbon dioxide, then you probably know that you did something right. Maybe you didn't inverse the molar masses. Remember, when you're dealing with amounts, you inverse the molar masses compared to the ratios that you have over here. It's only when you're dealing with diffusion time do you actually leave them in the same sequence. So you put MA over here or M molar mass of B.